Morning, everyone. Good afternoon, class. We are looking at Module 2, covering chapters 4 and 5. Chapter 4, Probability. Chapter 5, Discrete Probability Distributions. So here's Chapter 4, Probability. And we start with some definitions. A simple event versus a sample space. Anybody wants to read for us here, please?
A sample event is an outcome or an event that cannot be further broken down into simpler components.
Thanks. A simple event.
Oh, excuse me, yeah.
Continue, please.
Now, a sample space is a set of all possible outcomes or simple events of a probability experiment.
Excellent. If two events are mutually exclusive or disjoint, the probability that both will occur is 0. So event A and B are disjoint or mutually exclusive if they cannot occur at the same time. That is, disjoint events do not overlap. Probability of A and B is 0, or we may use intersection of events. This represents the intersection of events. Sometimes we actually spell out the and. So we may use and or the intersection of events. The probability of an event is always between 0 and 1. Probability of an event is defined as n of probability of A equals n of A over n of S is the probability of event A. And it can be 0, yes, can be 1, yes, but it can't go beyond them. Probability cannot be negative, cannot be more than 1 or 100%. The sum of probabilities of all final outcomes of an experiment is always 1. So when we add up the probabilities, the sum of the probabilities for all outcomes, we write down summation of P sub I, they must add up to 1. The only way they may not is when we do the rounding. So due to rounding, it may be a little bit off. When I say a little bit off, that means it can be that it's very close to 1 and a little bit larger, like 1.000001, many zeros before the 1, or it may add up to 0.99999, many nines, meaning it just happened due to round off error. We're going to look at the experiment as an example, rolling a die. And that gives us, as you can see, a common die gives us 6 outcomes, numbers 1, 2, 3, 4, 5, 6. And this would be considered the sample space for this experiment. A simple event would be any individual number, such as 1, 5, you pick it. A compound event would be any event having more than one outcome. Example, odd numbers would be 1, 3, 5. The number of combinations of n items selected n at a time is. So first, let's look at the definition of permutation and combination. Permutation is an arrangement of objects in a specific order, which means order matters. Example, the letter arrangements of ABC, we have 6 of those, are all counted separately as 6 different permutations. When n different items are available and all of them are selected without replacement, and that's the key. The number of different permutations or order counts NPR is n factorial over n minus r factorial. Combination is a grouping of objects, in which case order does not matter, which means all of them really are considered one. It's just ABC in some order. For combination, we use n factorial over r factorial times n minus r factorial, which is the same as the permutation divided by r factorial. So in this case, n is n and so is r. So we want Cnn, n factorial over n factorial times n minus n factorial. This is 0 factorial, and 0 factorial, like 1 factorial is 1, is just by the definition of a combination, and this becomes 1. It's the way you choose none given n items. If we go through the formula, the number of permutations of n items selected 0 at a time. Generally speaking, here's the formula: NPR is n factorial over n minus r factorial. In this case, n is n and r is 0. So basically, that is the meaning of it, by the way. If it's r items, n times n minus 1 all the way to n minus r plus 1 items. And in this case, when you put 0 here, you get n factorial over n factorial, because n minus 0 is n. So this also becomes n factorial, and the answer is 1. The thing I'd like to add is the following. When you look at a combination, you may write it in this format, or you may write it as n comma r. For the permutation, you might write it in this format. But the format that you see here is the format that is used with calculators. We will look at that later on. A pizza parlor offers 10 different toppings. How many 4-topping pizzas, different toppings, are possible? It's important to notice that order is not important here. If you are ordering a pizza and the first choice is pepperoni, or the second or the third or the fourth, makes no difference. Order is not important. It's a combination, and therefore we are going to use this formula where n is 10 and r is 4. So when we put it into this formula, we write 10 factorial over 4 factorial times 10 minus 4 factorial. This becomes 6 factorial. Now, on a normal basis, you can put it in a calculator to do the job, and it will give you the answer 210. However, if you want to know how to simplify it in case you're doing it by hand, I will show you how it's done when you are dealing with this case. So if you look at the bottom, you have 4 factorial times 6 factorial. I'm going to keep the bottom as 6 factorial. I'm going to go with the top and write down 10 times 9 times 8 times 7 times 6. And I'm going to stop and make it into a factorial. And then the 4 factorial, I'm going to write it as 4 times 3 times 2 times 1. So what happens? These two cancel each other. We notice 4 times 2 equals 8. So we can cancel that one. 3 cancels out the 9. And so we get 10 times 3 times 7 is 210. In other words, can it be done by hand? Yes, it's not that big of a deal, but you can do it with technology. I'm going to clean up so we can move on. Could somebody read this, please?
How many 6-letter code words can be made from the 26 letters of the alphabet if no letter can be used more than once in a code word?
Excellent. And because of the way it's given and because it's a code word, we use permutation since order is important. Order is important. So we are going to use the permutation formula, in which case n is 26 and R is how many letters we need. We put it into the permutation formula, 26 factorial over 26 minus 6 factorial, and that becomes 20 factorial. And as I said, you can write the top as 26 all the way times 21 and then 20 factorial. The 20 factorials cancel each other. Or you may even write it in this fashion anyways, because they can't repeat 26 times 25 all the way to 21. And it becomes a huge number, 165,765,600 possible codes. We want to answer the following. Could somebody read part A, please?
A quiz consists of 3 true or false questions. How many possible answer keys are there? Write out the sample space and tree diagram.
Perfect. N of S is the number of outcomes per stage. And we raise it to the power of number of stages. A true-false question has only 2 outcomes, true or false. So the number of outcomes in this case is only 2. How many stages? In this case, how many questions? So it's 2 cubed. That's how you know how many. A tree diagram is helpful. You start with 1, the first stage, true, false. This is the first question. And if the top branch is T or true and the bottom is F or false, you keep it intact because if you are consistent, it's easier to follow. So this is the first stage or the first question. This is the second stage or question number 2, and this is the third stage or third question. So with this branch, we have true as well as false, the same thing here. So if we had only 2 questions, we would stop here. But when we go to the third question again, true, false, true, false. So if we are reading this branch as an example, we would read a T, T, T. If we want to read this one, T, T, F. Then we go to this one, T, F, T, T, F, F. And that ends up giving us 1, 2, 3, 4, 5, 6, 7, 8, as expected. Different outcomes. Stage 1 or question 1, stage 2 or question 2, stage 3 or question 3. Now, this sample space is for tossing 5 coins. We want to know how many outcomes. Now, just like the true false, a coin has 2 outcomes, heads and tails, and there are 5 coins. Those are 5 stages. So it becomes 2 to the power of 5. So number of outcomes per stage. So each coin has 2 outcomes, tails, heads, and then how many coins? 5 to the power of 5. That's 32 different outcomes. Here's the tree diagram for 4 coins. Here's the first one, heads and tails. Second one, third one, fourth one. I didn't have room to add 5. I just wanted to make a point. Here's for 4. And I need to add, so this is stage 1, 2, 3, 4. I need to add 1 more. And if I just do one of them, you get the picture. It's heads and tails. Now I got to do for this one, for each and every one of them, I have to add the same here, which gives rise to a total of 32. And so if I want to go with the first one, I would read H, 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 H. There are 5 of them. For this one, I would read H, 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 T. And then I move on. For example, this one would be H, 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 and then you go to T, and then H and T and T. And therefore, you end up with the following sample space. On a normal basis, for 5 coins, nobody expects you to do that, but understand this is, we have 5 H's. If we go down at the bottom, we have T, 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 and 1 more T, we have 5 of those. What matters is understanding how many and why. How many and why. That is extremely important. Could somebody read this, please? Anyone?
All right, I'll keep reading. A random sample of 100 people was asked if they were for or against the tax increase on the rich people. Of 60 males, 45 were in favor, and of all females, 22 were in favor. Write the contingency table and answer the following questions. If one person is selected at random, find the probability that this person favors the tax increase on rich people.
Excellent. What matters is to be able to write the table properly. So the table, this is a contingency table. male, female, 4 tags against it. So we're going to give them letters to make it easier when we want to write the formulas. M represents male, F males or male, F for females, a T those who are 4 tax increase, and A against them. So a random of 100 people, that means this total must be 100. Of 60 males, that means total for males would be 60. 45 were in favor. So males, 60. They are in favor, 45. And of all females, they didn't tell us how many females, but they're saying 22 were in favor, so 22. So we plug in those values. We can figure out the rest. For example, total is 100 here. We have number 60 here, so this must be 40. Very simple. This is 60. This is 45. 60 minus 45. This must be 15. Now we said it's 40 here, minus 22 must be 18. Now add these two up, 22 and 45 is 67. You can add these two up or say 100 minus 67 is 33. So you can fill up the rest accordingly. So the very first thing is to come up with the table properly. Now this person favors the tax increase, so the probability of T, if you will, is N of T over N of S. This is by definition of probability. We should use a capital T here. So the total size is 100. I highly recommend when you deal with probability, first understand what is the sample space of interest. In this case, you're dealing with the whole table and it's 100. And N of a T, you look for T and you have 67. So this is what you have, 67. This person is a female. So probability of F is N of F over N of S. Again, the denominator is the whole table, the whole sample, so it's 100. Now, how many females? We have those two numbers, females. 22 plus 18, 40. You can read just 40 or just add up these two. Either way is fine. So the answer is 40 over 100, which means 2 over 5 or 0.4. By the way, again, this is an exact answer. This is an exact answer. That's fine. I'd rather keep it as a fraction or exact answer. If it's something you want to go with a decimal, you want to go in, and if it's not exact, you want to go as many decimals as they ask. This person opposes the tax increase on rich people, given that the person is a female. In other words, if this person is a female, she opposes the tax increase. This is another way of putting it. So the very first thing I want to discuss is the conditional probability. Probability of A given B is the probability of A intersection B over the probability of B. So these formulas are available to you. And the same token, probability of B given A is the probability of A intersection B over P of A. This is in general. Of course, when they become independent, it's a different story. I'll go over that in a moment. But for now, we want the probability of A given B in general. In this case, this person opposes the tax increase on rich people, given that the person is a female. So after the given comes F, That's so B is replaced with F, and opposing it is A. So probability of A given F, we're going to write probability of A intersection F over probability of F, which in essence becomes N of A intersection F over N of F. What do I mean by that? I want everybody to pay attention to this so you never make a mistake. You will always look at what comes after given. This line segment is read given. After that comes F. That is the sample space. The whole sample space was 100. Now we are only dealing with females, so it has shrunk to 40. I always start with the denominator. The denominator is 40, therefore. Of those females, in other words, just this group, this person opposes the tax increase. How many? 18. So 18 over 40. 18 over 40 simplifies to 9 over 20 or 0.45. Conditional probability, probability of A given B. This person is a male, given that he favors the tax increase on rich people. So what comes after given? Favors, that means T, and before that is M. So probability of M given T. And it becomes, according to this formula, probability of M intersection T over probability of T, and ultimately becomes N of M intersection T over N of T. And I start with the denominator, which means after the given, how many are in favor, right after the given? How many are in favor of the tax increase? That is a total of 67. Of those 67, so we are just dealing with this group, out of those 67, we are looking for the number of males. And that makes it 45. So 45 over 67. To write this, you can write 45 over 100. This is if you go with the probability. This one is 67 over 100. That is a complex fraction. They cancel each other. We get 45 over 67, which is exactly what we have here, which is the number that is in common between the males and those who are in it for tax over the total of those who are in favor of that. And of course, over here, we have used 4 decimals. Remember, it has been truncated. We have many more decimals, and at the very least, you want to go with 4 or just follow what they ask you. We are going to move on with the same table, and now this person is a female, and it's the intersection of events. Favors the tax increase on rich people. First and foremost, the only time that the sample size, which is 100, shrinks if you're dealing with a given or a conditional probability. Otherwise, it's always the original size, which is 100. Now, in this case, we want to go with probability of F intersection T, and that is N of F intersection T over N of S. As always, I like to start with the denominator, which is total of 100. Now we're going to look for these two groups and find what's in common. F stands for the females. So we are in this category, if you will. And T is here. So this and this, number 22, is both, belongs to both group, females and those who are 4 tax increase. So 22 over 100. It simplifies to 11 over 50 or 0.22. So that's an and statement, intersection of events. What's in common? This person opposes the tax increase on rich people or is a female. We are looking at the probability of A union B, which is probability, generally speaking, probability of A plus probability of B minus the probability of A intersection B. In this case, we are looking for probability of A or F. A union F. Opposing tax increase, the A group, females, the F group. So A intersection F is probability of A plus probability of F minus the probability of A intersection F, because this is accounted for 2 times, once for P of A, once for P of F. And again, you have this or addition formula for probability. So N of A over N of S is the first one, N of F over N of S for the second one, and N of A intersection F over N of S. I want you to understand the concept from the point of view of formula, and then you can easily understand what happens here. Now, what this means, look at the A group, and A group, we have a total of 33. That's what this is. Then the F, we have a total of 40. But between the two, what's in common? 18. What does it mean? 18 has been accounted for 2 times, once for this group and once for this group. That's why we take it out once. We add them up, 33 over 100, 40 over 100 minus 18 over 100. We get 55 over 100, which is 11 over 20 or 0.55. Are the events females and opposes the tax increase on rich people independent? Let's look at the definition of independent. If we look at these two and we do the cross product, you put a 1 here, and you could do the cross product here. You put a 1 here, you do the cross product, and it gives rise to this formula algebraically. I hope everybody is following that. So to show you, probability of A intersection B is this, probability of A given B times probability of B. Or in this case, probability of A intersection B is probability of A times probability of B given A. So that's the definition of probability of A intersection B. Now, events females and opposes the tax increase on rich people are dependent because occurrence of one of the events does not affect the other event. So what does it mean? It's really very hard to follow that, but we can do that with formula. That's why I'm big with formula. So how do you prove dependency? You look at the conditional probability. If 2 events are mutually exclusive, so if they are independent, if 2 events are independent, then probability of A intersection B simply becomes probability of A times the probability of B. Because if they are independent, I will continue here. If independent. Probability of A given B becomes probability of A. So conditional probability becomes marginal probability, simple probability. And probability of B given A becomes probability of B. And instead of going over the definition, which is vague and doesn't really mean much, we can prove that by looking at probability of A given F, because we want to look at their independency. Females and opposes, A and F. So probability of A given F, probability of A given F is 18 out of 40. But probability of A is 33 out of 100. Since they are different, they are not independent. It makes them dependent. Now, I suggest you try probability of F given A. So I'm going to write it down, try finding the probability of F given A. See if it's equal to probability of F. And by the way, you don't have to do that because we've already proved it, but this is for practice. The next part is asking, are they mutually exclusive? And again, they are not mutually exclusive because a person can be both female and oppose the tax increase on rich people. But again, the best course of action is to look at the proof with formulas. Probability of A intersection F, we know it to be 18 over 100. Here's the F group, here's the A group, and common between the two is 18. 18 over 100, is it 0? No, therefore they are not mutually exclusive. So we prove that with numbers, with formulas, and that is extremely important. Let me fix this one. Okay. Let's look at the following example. Find the probability of getting the outcome of tails and 2 when a coin is tossed and a die is rolled. We assume independency. Therefore, the probability of a tails and 2 is the probability of tails times the probability of 2. If 2 events are independent, probability of A intersection B becomes probability of A times probability of B, as it was mentioned in the previous page. Tails, 1 out of 2, probability of 2, 1 out of 6. Their product is 1 over 12. A classic counting problem is to determine the number of different ways that the letters of personnel can be arranged We want to find the number. So first, the explanation about this permutation rule. Could somebody read this for us, please?
The permutation rule.
Please.
Okay. Permutation rule. When some items are identical to others, the number of different permutation order counts when n items are available and all n of them are selected without replacement, but some of the items are identical to others is found as follows. N1 are like n to the power 2, or do I just say n2?
N sub 2. N sub 1 are alike, N sub
Okay.
2 are alike, all the way to N sub k. We have this formula. Excellent. Well, we look at this and we notice that we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 letters. N is 9. Then we look at P and say P is one of them. E, we have 1 and 2. And we do that for all of them. We end up with the following. N is 9. P, we have only 1. E, we have 2. R, we have 1, all the way to the end. And following this, we replace the N with 9, and then we put all of this with factorial at the bottom. 1 factorial, all of them are 1. 2 factorials is 2 because it's 2 times 1. So the bottom is really 4. You do the division and you end up with 90,720 permutations. Ways of writing words with personnel. A box consists of 14 red and 36 blue markers. If we select 3 different markers randomly, what is the probability that they are all red with replacement? Well, we see that the probability of a red 1 would be 14 out of 14 plus 36, which is 14 out of 50. So N of R, so P of R is, R stands for red, is N of R over N of S. We have 14 over 14 plus 36, or 14 over 57 over 25.20. These are different ways of writing it, but this is important to understand how we arrive at it. 14 is the number of reds, and this is the total. Now, we want all of them to be red, and because it's with replacement, each one has the same probability. So, probability of 3 red is the probability of R1 intersection R2 intersection R3, and because it's with replacement, it becomes independent. So probability of the first one is red has got nothing to do with the second or the third one. So just multiply them, and each one is the same amount, 14 over 50, or 7 over 25, or 0.28 to the third power. So probability of 1 red to the third power. Why is that? With replacement means independent events. So just multiply them through. And 7 over 25 to the third power. And notice I put all the decimals because I can come up with that, and it's not an irrational number that continues indefinitely. So I like to put all the decimals, or you can write them as a fraction. Either way is fine. But if they ask you to, so if they said write them as a fraction, you can do that. If they say use decimals with so many decimals, you want to follow that. What is the probability that they are all red without replacement? And draw a tree diagram and label each branch. First of all, Most of the time, this is what we end up with. I want you to know that. In other words, if they don't mention with or without replacement, that means without replacement. That's extremely important. So now we want probability of 3 of them being red. That means probability of red 1, the first one, times the probability of red 2 given the first one was red 1, and probability of the third one being 3 where the first 2 were red, R1 intersection R2. That's really the proper way of writing it. If you don't write it that way, it's not that big of a deal. But understand, this is obviously the same as this one is 14 over 50. The first one is 14 over 50. But remember, we are not doing it with replacement. So first and foremost, the total of 50 goes down to 49. There were 14 reds, then it goes down to 14 minus 1. Then the next one, 50 minus 2, and then the next one, red 14 minus 2. In other words, 14 over 50, 13 over 49, or 12 over 48. That's how you come up with the answer. You can go through the process of dealing with the fractions for the sake of argument. You know this is gone and this is 4. You know this is divisible by 7. This is divisible by 7. You know this is gone to 1. And this is 25. So you can simplify it easily. Write it as a fraction, as a decimal, it's up to you. And let's look at the second method as well as the tree diagram. You can write probability of all 3 red is n of all 3 red over n of s. Let me write it in this fashion first, perhaps. That would be helpful. So this one, you can write it as n of all reds over n of s. All possible outcomes. First of all possible outcomes, we have a total of 50, and out of 50, we want to choose 3. Order is not important, combination of 53, that would be your denominator. But what do we want? We are looking specifically for red, so combination of 14, because there are 14 red, we want to pick 3. So combination of 14, pick 3. That would be how many reds? And combination of 50, choose 3, that would be how many possible outcomes that have everything in them, not necessarily all red. And here's the tree diagram I want you to pay attention to. Again, the first stage, look at the first stage. The top is red, the bottom is blue. Let's say we're going to continue with the top being red. And this would be 14 out of 50. This would be 36 out of 50. And I'm not going to simplify it. I want to keep it intact. You'll see in a moment why. So when I go to the second stage, meaning choosing the second one, the top branch, over here it was red. When I go to the top branch, 1 red is gone. First of all of them have the denominator 49 because it's without replacement. Secondly, 1 red is gone. How many is left? 14 minus 1. But if you go to this branch, because it's blue, how many blue is gone? None, so you have all of them, 36. Now when we go down here, blue, how many red is gone? None of them, so we have 14 out of 49. But if we go to this branch, 1 blue is gone, so out of 36, the numerator becomes 35. But notice all denominators are 49. When we go to the next stage, the third one, first and foremost, all of them have the denominator 48. Then if you look at the top branch, we had 14 red, then 13, now 1 more is gone, so 12. but the blue, all of them are intact, 36, and the rest of them fall. If the probability of winning the race is 5/12, what is the probability of losing the race? Clearly, we are going to use what's called a complement. Probability of A naught or A bar or A complement is 1 minus probability of A. So probability of winning is given as 5/12. So probability of losing is 1 minus that. I'm going to call it L. And 1 minus 5/12 is 7/12. So you want to justify everything properly. What are odds against winning? So let's look at the definition of odds. The actual odds against event A, we put O as odds and we put A complement or A naught or A bar is probability of that, probability of A bar over probability of A. And we express it in form of A colon B or A to B, and they are integers. We don't simplify, we don't use decimals. Okay, we may use fractions, but we use them with integers. So with that being the case, odds against winning, that means odds for the losing, would be probability of losing over the probability of winning, which is 7/12 over 5/12. This is a complex fraction, and it becomes 7/5. You can write it as that as fine, or you can represent it in this format, 7/5. If the payoff odds is listed as 6/1, how much profit do you make if you bet $10 and you win? Here's the definition of a payoff odds. The payoff odds against an event A is equal to net profit to the amount of bet. That is the ratio of the two. In other words, payoff odds against event A is net profit divided by the amount of bet. And therefore, net profit would be the product of these two because this is a fraction. You can do the cross product. So net profit is the product of these two. In this case, we have the product of 6/1 means 6. If it was 6 to, let's say, 7, it means 6/7. Okay, whatever this fraction is, this means 6 times 10. The product is $60. That's how much we win. Could somebody read this page for us, please?
When two different people are randomly selected from those in your class, find the indicated probability. Assume birthdays occur on the same day of the week with equal frequencies. Probability that two people are born on the same day of the week. And the probability that two people are both born on Monday.
Excellent. We want to distinguish between the two, and that's really the key. In the first case, no particular day is specified. The first person can be born on any day. Probability of the second person born on the same day is 1/7. So therefore, the probability is simply 1/7, or you can say 7/7, because there's no particular day for the first person. And the second person has the probability of 1/7. The product is 1/7. Now, what is the difference between this and a specific day. By the way, it doesn't have to be Monday. You can choose any day, Tuesday, Wednesday, any day that you choose. The next one works in the same manner, which means probability of the first person born on that specific day, whatever that day is 1 out of 7. The second person, the same thing, 1 out of 7, because we are choosing a specific day. And therefore, the probability that both have a birthday on Monday is the product of the two, because they are independent, and it's 1 over 7 times 1 over 7 equals 1 over 49. How many different auto license plates are possible if the plate has, let's see, 2 letters followed by 4 numbers? So there are 6 spots, 1, 2, 3, 4, 5, 6. So we have 2 letters. So this can be any letter, 26. This can be any letter because there is no restrictions. And then the next one is a number, 10, 10, 10, 10, because 0 to 9 is 10, by the way, right? 0 to 9, 10. That's why we call it decimal system. So 26 squared times 10 to the power of 4. Needless to say, everybody can plug into a calculator to figure it out. I want to show you how we arrive at the answer. So if we were to write it 26, 26, 10, 10, 10, 10, that's how you would do that. Now we have, in part B, we have 3 letters we can't repeat. And then we have 3 numbers. So that means we can have 26, then we go to down by 1, and then we have numbers. So we have 26 times 25 times 24 times 10 cubed. Now we can have 4 letters. Repetition is okay. And then we have 2 numbers where we cannot repeat. Right? And then the numbers, we have 10 here. Since we cannot repeat, the next one can't be 10, has to go down by 1. And so the answer is 26 to the power of 4 times 10 times 9. Those are the possible outcomes. The next one, we're going to have only 4 places. Each character is either a letter or a number. As you know, if we go this route, we have only 4 spots. And now we have 26 plus 10, 26 letters plus 10 digits. We do have 36 characters. Which makes it 36 to the power of 4. In a first grade school class, there are 10 girls and 8 boys. In how many ways can the students finish first, second, and third in a foot race? Assume no ties. Clearly, order is important because we said first, second, third. And it uses permutation P and R. And we have total of 10 and 8, 18 students. So we want to choose 3 of them, first, second, and third. So one way you can say there are 18 ways for the first one. Then we go down to 17 to 16. This is one way to do that. You may use the information here as to what command you need for a TI calculator. You can press math, probability, NPR. You have to choose the 18 first. And if you do that, 18 NPR3 gives you the number that you're looking for. The answer is 4896 for this. Again, more importantly, we want to see how we arrive at it. This is important to understand why. Now in part B, the girls finished first and second in a geography contest. So now we have, again, the case that order is important, which makes it a permutation, but we are dealing with only n being 10, and we are choosing the first and second. We are choosing only 2. So permutation 10, choose 2, or 10 times 9, which is 9. Three boys be selected for launch duty. Well, nothing is specified. Order is not important, which makes it a combination. Order is not important. So we're going to go with the combination. And boys, we have 8 of them, choose 3. Combination of 8, choose 3, which is 8 factorial divided by 3 factorial times 8 minus 3, which makes it 5 factorial. And you can come up with the answer simply as 56. Now we want 6 students for a team, a hockey team. So we have total of 18. Order is not important. So that makes it a combination. And the combination, we are going to use N as 18 and R as 6, which is N factorial, 18 factorial, over R factorial, which is 6 factorial, times 18 minus 6, 12 factorial. That's as far as how you set it up. And you can use a calculator, 18 NCR6, and it gives you the answer. So you can use a calculator, but it is the concept. This is extremely important to write, not just the answer. 5 students be selected. 3 boys and 2 girls. In that case, if we just stick with 3 boys, that means out of 8, we want 3. Order is not important. That's a combination. And 2 girls, out of 10, we want 2 girls. That is also a combination because order is not important. And we multiply the 2, which means C8 3 times C10 2. Now, this is 8 factorial over 3 factorial times the difference, which is 5 factorial. This is 10 factorial over 2 factorial times the difference, which is 8 factorial. As far as setting it up, you can easily drop those 8 factorials and then write out this one as 1 times 2 times 3. Keep this writing 10, 9, 8. 7, 6 times 5 factor and drop it, or just plug it into a calculator, 25, 20. It's not a big deal. Use a calculator. This is the important part, telling your reader how you arrive at it. This is what must be written. 4 girls be selected for a field trip. Obviously, order is not important. So from N equals 10, we're going to choose R equals 4. It's a combination. 10 factorial over 4 factorial times the difference, which is 10 minus 4, 6 factorial. You work it out and you get 210. Could somebody read this, please?
In a lottery game, a player picks 5 numbers from 1 to 48. If 4 of the 5 numbers match those drawn, the player wins second prize. What is the probability of winning this prize?
Excellent. So we write the probability. The probability of winning, W stands for winning, is N of winning over N of S. How many ways we can win over how many ways we can pick things in general. So first, I'd like to discuss the denominator, as I've said before. So I want to come up with N of S. N of S, we are picking 5 numbers from 48. That's what we want to do. Order is not important. We just want to pick 5 numbers. And that makes it a combination. Combination of 48. N is 48. R is 5. Combination of 48, pick 5. 48 factorial over 5 factorial. The difference between 48 and 5. That means 48 minus 5 or 43 factorial. That is the way you calculate it. It may be a huge number. It's not a big deal. I'm showing you how it's calculated. Now, we want to calculate N of winning. How do we win? Let's go back, see if 4 of the 5 numbers match those drawn, which means we want the possibility that 4 is correct and 1 is incorrect. So N of W is N of 4 correct and 1 incorrect. Again, order is not important. So how do we get 4 correct? Out of 5, we get 4 correct. That means combination of 5, choose 4. Now, the rest of them, 48 minus 5 is 43 numbers. From that, we're going to pick 1. So this is combination of 43, pick 1. And so N of winning is 5C4, combination of 5, choose 4, and times combination of 43, choose 1. That is the top, and that is the bottom. So I'm going to put it in here. By the way, 43C1, this is 43, and this is 5. And this one, you need to put it into a calculator, and you can simplify it to 215 over, let's see what we have here, 1,712,304. And of course, you can write the decimal. They may want it in fractional format. You should be able to write that accordingly. Could somebody read this, please?
A poker hand consisting of 5 cards is dealt from a standard deck of 52 cards. Find the probability that the hand contains exactly 2 face cards.
Excellent. All right, so we want the probability of 2 face cards. We want the N of 2 faces over the N of S. Again, I like to start with N of S. We have total of 52 cards, and we want to pick 5. That would be N of S. So order is not important, becomes a combination. So from 52 cards, we're going to pick 5. That is the denominator. And we write it 52 C5. So 52 factorial over 5 factorial, 52 minus 5 factorial, or 47 factorial. Then we want 2 face cards. So what is N of 2 face? We want n of 2 face cards and 3 non-face cards. That's really the idea. We want 2 face cards and the rest of them are not. The face cards are Jack, Queen, and King. And times 4, because we have 4 suits, there are 12. 4 suits, 3 times 4 makes it 12. And so we have 12 of those. The rest of them, 52 minus 12 would be 40 non-face. So how do we find this? N of having 2 face cards. Combination of from 12, choose 2. Combination of n is 12 or is 2. Times combination of 40, pick the rest of them, 3 more cards. So this would be n of 2 faces. One more time. We want only 2 faces. So there are 12, choose 2. It's a combination because order is not important. Times the rest of them, we have 3 more cards come from the other 40. Combination of 40, choose 3. So now we put this at the top. We put this at the bottom. We go back to this. We put it right here. And it's just a matter of simplification. You can calculate each one, simplify the fraction, however they ask you. And I'm going to assume you continue in the process that they ask you. In this case, if they ask specifically in a fractional format, you have to simplify as much as possible. 209 over 833. Could somebody read this question, please?
A factory received a shipment of 16 sprockets, and the vendor who sold the items knows there are 7 sprockets in the shipment that are defective. Before the receiving foreman accepts the delivery, he samples the shipment, and if too many of the sprockets in the sample are defective, he will refuse the shipment. If a sample of 7 sprockets is selected, find the probability that all in the sample are defective.
Excellent. So if we want to find the probability, we're going to write the formula. The probability of all being defective is n of all being defective over n of s. That is the formula for probability. Now, again, I like to start with the denominator. We want to pick 7 out of total of 16, and order is not important. So the denominator is combination of 16, pick 7. So that's the denominator. The numerator, all of them defective. So we are going to pick 7 out of 7. That means combination of 7, choose 7. This is the n now. This is the r, pick 7. Combination of 7, 7. This is n, this is r. In this case, n is 16. 7, 7. Times, now the rest of them, there are 9 of them that are not defective. If we want all of them to be defective, there is nothing left. So combination of 9, choose 0. That's their product. And this is 1, this is 1, and this has to be calculated. And this is what you end up with if you want to use a calculator. Basically, you would calculate the denominator. CNN is 0. We went over this, so it's a good practice to know CNN is 0. CN0, my apologies, 1. And CN0 is also 1. So that's why the numerator is 1 times 1. But you can calculate. It's not a big deal. You can even use a calculator, put it into a calculator, but it can easily be figured out. We looked at it in the beginning. Now, if a sample of 7 sprockets is selected, find the probability that none in the sample are defective. So again, the formula n of non-defective over n of s. N of s is the same that we got here. Combination of 16, choose 7. So that's not a problem. None is defective. So here, out of the 7, we don't want anything to be defective, so choose 0. And this one, 9, you have to choose all of them, all 7. So 9 combination 7. So that's what happens here. So 7 combination 0, 9 combination 7. This, of course, is 1. This one you put into a calculator. You put into a calculator. You end up with 36 here, 11,440 here. So the ratio of the two is the answer. You can drop the top and the bottom by a common factor of 4, and it becomes 9 over 2860. If need be, you can represent this with a decimal.